Okay, recording has started, and here's the practice quiz. This is a little lengthier than normal, so I'll give a little more time. Alright, anybody still need more time? Happy to give more time if you need it. Alright, so we'll go ahead, and the first thing I would look at in a problem like this is, can I solve for y and isolate the y and turn it into an explicitly defined function? And there's no way, because one of the y's is combined with x, the other is inside a sine of y. You can't isolate the y. So I'm going to take d dx of both sides. So this is the verb. It's the action of take the derivative with respect to x. When I distribute that to the xy, I got to use the product rule. So it's the first times the derivative of the second. d dx of y is the same as dy dx plus the second times the derivative of the first. But when I take the derivative of x, I get 1 plus, and then this derivative is 6x squared is equal to, and when I take the derivative of the sine of y, I get cosine of y. Derivative of sine of something is cosine of that thing. Then chain rule, since this letter and this letter did not match exactly, I have to chain on y is some function of x. I have to chain on dy dx. Alright, now, I'd like feedback at this point. Are you comfortable getting to this point right here, or is this the trickiest part for you? Getting to this one right here. Let me just check the feedback. Everybody give me a little feedback on this. Alright. So then we're going to move all the terms that contain dy dx to one side. So all I'm going to do is move, and you can do it in either way, but I'm going to move this term over here. So I'll have y plus 6x squared equals cosine y dy dx minus x dy dx. I'm going to factor out a dy dx. And what I'm going to be left with is cosine y minus x. And then this should be on the left, but I'm going to move it over to the right. You can write an equation, a equals b, b equals a, in either order. I'll put the 6x squared first plus y. Then I'll divide by what's in parentheses. And I'll get dy dx. Okay, and if there's any other feedback you'd like to give me on this, I'll look at it, but perhaps the feedback you've given me so far is plenty. Let me just take a look. Okay, and all right. That's the only practice quiz problem relating to implicit differentiation. We're going to go on to some practice quiz problems that's kind of introducing the new material. Let me just check for any other feedback though. All right. Let's go to number 2. Start with 2a and 2b. Might have been a long time since we worked with these, so see what's coming back to you. Okay, anybody need more time? Let's look at 2a. What a logarithm asks is, what is the exponent that I put on the base of this 2 to get this result of 8? and that exponent is 3. Again, it's asking you for the exponent to go on top of that base to get that result. Okay. Now, on part B, we're going to look at this 2 different ways. One way we're going to look at it is we're going to isolate this thing that I'm going to circle. Let's look at that for a minute. It's asking, what is the exponent that I put on top of 2 to get 7? Now, when we think about that, it has to be a little bit smaller than 3, because 2 to the third is 8, so it's going to be like maybe, I don't know, 2.8 or something like this. But now we put that exponent on top of the 2. So it kind of feels like circular reasoning, but it isn't. If you reason your way through it, you have to get 7. Because it's the exponent on top of the 2 that'll give you 7. Now you're putting it on top of 2, so you have to get 7. So you can reason your way through it this way. You can also see it like this. Logarithm, base 2, exponential function, base 2, are what we call inverse functions. 2 functions that are inverses do each other in, and all you'll be left with is 7. So that's a quicker way to look at it. You don't have to think as hard about it. You just say, oh, these are inverse functions. They kill each other off. All right, so now this is very important feedback. Let me know, has it been a really long time from logarithms for you, and like, is it like you really need refreshing from ground zero, or no, you're pretty good with this? I remembered most of this. I'm ready to go. Give me feedback with logarithms. And Kylie, yes, after class. We can hang after class. Okay. Alright, so I am going to start with ground zero, but I'm going to go real fast today with logarithms when we get to that part. Alright. And it's renumbered, all these things. They're all numbered. I don't know why I number these carefully. Every time I make any kind of, put some extra space between items, it renumbers everything. Alright, go ahead and write 8 as a base to a power with base 2. Let me give you a quick 30 seconds for that. Rewriting 8 as a base to a power with base 2. So this one, the base is 2, base to a power. It must be 2 to the third, because 2 to the third will give you 8. So we rewrote 8 as a base to a power with base of 2. Now do it again for 27. Okay, and this one, the base is 3. 3 to what power? 3 to the third is 27. Alright, let's go to the next number 1. Write 9 as a base to a power with base 2. This one you're going to have to think about. All right, I'm going to have you stop. Take a moment and consult in your groups. See which ideas you can come up with there, and I'm going to call on a group in a minute. Okay, group 4. What do you got?
Log to the base of 2, 9?
So I have 9 equals 2. What do I write
Oh,
next?
wait, I don't get what you're asking. I'm sorry.
Okay, repeat what you said. I think you said something that was helpful.
Uh, I said log to the base of 2 and then 9 right next to it. Yeah.
Okay. And remind me who you are again?
Josh.
Josh. Okay.
Yeah.
All right, so log base 2 of 9, right? 9 as a base to a power with base 2. I think this is kind of related to that. But let me, this would be 2 to the x, 2 to what power is equal to 9. So 9 to the base 2. So you're on the right track. This would give us something like this. But we can also do it with the pattern that we've been using so far. So just like we did 8 as 2 to the third, we can write 9 as 2 to some power. And what is the power that I have to put up here? One answer to that would be, well, it has to be a little bit bigger than 3. Because if I do 2 to the third, I'm going to get 8. So maybe it's 3.2 or something like this. But I can get it precisely. How I can get it precisely is by putting the thing that you were talking about, Josh, right up here. What's going to happen is 2 and log base 2 are inverse functions. They're going to kill each other off. And so I'm going to get 9. And it's also causing us to think in this really strange way. Remember, this is asking 2 to what power will give me 9. It'll be that 3.2 approximately thing that we were thinking about. 2 to what power is going to give me 9. Now raise 2 to that power, and I got to get 9. So we can change the base to whatever base that we want to by using this strange little inverse idea here. So we wind up doing this quite a bit because in calculus we're going to prefer that all exponential functions have base e. And so that takes us to our last number 1 here, which is right 9 as a base to a power with base e. So let me give you a moment to ponder that. And once again, consult in your group. And there's a kind of an efficient way to write this too. I'll call on a group in a moment. Group 6, what do you got?
What about 9 equals e to the ln power?
To the ln 9. That is correct. ln means log base e. And so that's the shortcut notation for log base e. E and ln would kill each other off, and we would wind up getting this. And if you have a calculator here, I want you to play around with your calculator for a moment. And you can also use a calculator on your computer. And type in ln 9. When I do that, I get 2.197, so on. And then if I did e to the x, e raised to the, and I typed the first few digits of that, 2.197, let's say that's all I put in. I'm going to get something really close to 9. I get 8.9979. All right, so we can see that these things allow us to change the base, and we'll want to prefer base E, and it's this little maneuver that we'll do to change it whenever we need to. So the section that we're going to be getting into today is inverse, exponential, and log functions. The reason why we're doing that, and it's from chapter 1, is that the section right after this is 3.9 derivatives of logarithmic and exponential functions. And so when you're dealing with the derivatives, you need to have the basics down. Oh, how did exponential and log functions work? How did we solve those equations and all that kind of stuff? So I saved the review on this to be just in front of the section on the derivatives so that you can kind of tie all this together. All right. Questions on homework or on the practice quiz or on anything at this point? All right, let's go to 35 to start with. All right, now this one, I would try to solve it for y if I could, but it's not going to be easy. And first thing I might do is cross multiply. So x cubed times x minus y is the same as x plus y. I could take the derivative d dx on both sides right away, but then I'm going to have the quotient rule. Now, doing it with the quotient rule is so complex that you'll get a very complicated answer. You will get a very different answer when we do it this way. It'll wind up being equivalent, but you won't be able to recognize it. It'll look so much more complicated when you do it with the quotient rule. So this will be preferable. I would probably, now again, you'd have your option. I can take the d dx of both sides right now and use the product rule, but I think I'd rather do this. But you know, different people will choose different ways to work it, and it'll be almost the same as if I work it that way or this way. Okay. And now This is about as simple as I can get it. Can I actually solve this thing for y? I think I could. I could put all the y terms on one side and all the other terms on the other side. So this one, I'm going to do it two ways. This could be very instructive. If I did it with implicit differentiation, let me show you what I'll get. And then let me come up here. I'm going to do the product rule. First times the derivative of the second plus the second times the derivative of the first and when I take the derivative of the right hand side I get 1 plus dy dx. Okay, and then distribute the minus sign. Bring all the dy dx's to one side. Let me bring this over here. So on the right hand side I'm going to have, and this 1 I'm going to bring to the other side. So on the right hand side I'm going to get dy dx plus x cubed dy dx. And on the left side I'm going to get 4x cubed minus 3x squared y minus 1. And so then let's come back over here. I'm going to factor out dy dx, turn the equation around. Dy dx, and when I divide both sides by what's in parentheses, I get this. That's a legitimate answer. That's the answer we get when we use implicit differentiation. Now, let's go back to this point right here. I could have done this with when I have x to the fourth minus x cubed y. I could have actually solved this for y. Most of these problems you can't, but this one, see, because if I move this to this side, move this over here, I'm going to have x or y plus x cubed y equals x to the fourth minus x. And then factor out a y. And then divide. So let's go back over here. Y equals x to the fourth minus x, or 1 plus x cubed. Now, dy dx. This is going to give me a better answer. It's going to look more complicated. This answer looks nice and compact. This one is probably going to look worse, but it'll be a better answer. Why will it be a better answer? Because it will only have the input variable. So if somebody asked you later, what is the derivative when x is 5, when x is 6, when x is 7, when x is 8? Well, on each one of those you had to go back and solve for y as your first step. And then plug them both in. But on this one, we'll only have to deal with the x's. So now you use the quotient rule, and it's the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And then we'd simplify this down, so on. But that would be an actually, in most cases, a better answer than this one over here. Bianca, does that answer your question?
Yeah, but I used a point. I used 1, 0 because I solved for a y for the point, and I got a different number when from the book answer.
Alright, so why did you use a 0.10?
Because I wanted to check my work and to see if
Oh,
the
okay.
equation.
So you said, alright, if x is 1, then the y is going to have to be 0. Alright, that seems to make sense when I plug them into the original equation, because 1 cubed is equal to 1 plus 0 over 1 minus 0. Okay, and when you plugged it in, you got a different derivative than what the book got?
Yeah.
Ah, that's a very clever way to check your answer. Good work. That does tell you that something is amiss between the two then. So what answer did you wind up getting, Bianca?
I got the same answer you did when you used the implicit differentiation.
So you got this answer right here. Okay.
Yes.
And when you used 1, 0, every time you see the x, you put 1 in. Every time you see the y, you put 0 in. We should get 4 minus, we should get 3 over 2. Okay. And what did the book get for their answer?
I think at the time I made an error because I got 2 over 2. I think I just made I wrote it the wrong way. That's probably why.
Okay, so maybe now it'll check with the book.
Okay. Thanks.
Good. All right. So any other questions on this one? Everybody good with 35?
I had a question about, I also did it the way you showed us right now. And then, of course, the book the book looked like they used the quotient rule.
Oh, they did the quotient rule. Okay, so it was very more complicated, right?
I think all the answers in the book, I think, are quotient rule based. But
Okay.
I guess my question is why do they, I mean, I understand that they look different, but how, like being so different, yeah, I kind of did what Bianca did where I had to plug in several points just to make sure I had the right equation. But can you explain why they look so different, and is there some way to manipulate them where they are the same?
It's all right. It's not going to be easy to tell that they are the same. probably the only way that you're going to be able to check is exactly what you guys are doing, putting in some points, because they can look so very different. And that's this one, you could check on this one only because we were able to solve this thing for y. When I did the y and I get this, when I get this all reduced down, and then if I plug that y, or even if I plug this y in for this y right here, I could kind of show that they're equivalent, but most of the time you can't. So I think what the textbook, you see, most textbook writers, they don't create their own solution manuals. They hire graduate students to, work out the problems and put in the solutions. And it could have been that the graduate students were kind of figuring, well, most students would use the quotient rule, so we'll just go ahead and use the quotient rule here. But really, that's not the most efficient way. It's a much longer, and you get a much more complex answer. That'll be equivalent. When you plug in the numbers, you'll get the same thing in the end, but you really can't verify that very easily at all. All right, good questions. I think there was something else. 70, there was multiple people on 70. Let's look at that. And find by implicit differentiation, solve. All right, let me snip this whole thing. Once again, I would try to simplify this. Well, how would I do this one? I'd have to think about this one. I got to find dy dx. One way you can find dy dx, you can solve this explicitly for y by taking the square root of both sides. If you do that, what you wind up getting is y equals, but you have to put a plus or minus. And plus or minuses are kind of awkward to work with. Now the square root of the x squared on the top becomes just x. We could do this, and then you don't even have to use implicit differentiation. But you're going to have a plus or minus in there. And a number of people would rather have their answer with implicit differentiation, have the derivative contain y, rather than contain the pluses and minuses. And that's whenever you have, your output variable to an even power, you would have that difficulty. So, but you don't have to do it at this point. You could cross multiply first, but then you're going to get dy dx in two different places. This one, I might do this one by using the quotient rule here. So if I did d dx of y squared equals d dx of the whole right hand side. And then I'm going to get 2y dy dx So notice you only get one dy dx, so that part's going to go really quick. When I get this answer on the right hand side, although it'll be complex, all I'm going to have to do is multiply both sides by 1 over 2y, and I'll have my final answer. And so then this right hand side, this is, now I probably would change this to 4x squared minus x cubed. So I wouldn't have to use a product rule here. Okay. And then I would simply, now it's the quotient rule. So it's the bottom times the derivative of the top. Minus the top times the derivative of the bottom over the bottom squared. Okay, and then I would FOIL out in the numerator and combine like terms. When I multiply the 4, I'm going to get, what, 32x minus 12x squared. When I multiply the x, I get plus 8x squared minus 3x cubed. So that replaces all of this. And then, so my dy dx, when I put all these together in the numerator. Now this, let's go back to here, I'll distribute this minus sign. Alright, so the 32x doesn't have any like terms. Minus 12x squared plus 8x squared is minus 4x squared. And another minus 4x squared makes minus 8x squared. And then I have this minus 3x cubed plus 1x cubed is minus 2x cubed. Over 4 plus x squared. But I multiply both sides by 1 over 2y. So it puts a 2y down in the denominator over here. And then the only last thing I would do is factor out a 2 in the numerator and then cancel that with this 2 over here. Basically that would be the answer for A. And then solve the given equation for y to identify implicitly defined functions. Alright, so part B says to do this. And then use the function from part B to graph, and then B, you just put this like into Wolfram alpha or so, and then graph it to graph the given equation. Alright, is that enough on number 70? Or are there any questions, or anybody wants me to do anything more with that?
I don't understand part B that well.
Okay, so part B, to solve the given equation for y, this one right here was almost already solved for y. It was just y squared. So, to solve it for y, we just take the square root of both sides. But when you square root of both sides, you have to introduce the plus or minus sign. So that's why we came up with this equation right here for when we solved it for y. So that's all you have to do for part B. Solve the given equation for y to identify. Now, why they called it F1 and F2? Well, there's actually going to be two different ones. One of them is plus, and the other one is with the minus sign. So that's why they said with this.
think it's just.
Pardon?
I think that those two just kind of threw me off, so that's probably why I didn't really understand it well.
Okay. It kind of threw me off too. I wasn't sure what they meant until I figured, oh yeah, it's probably one of them with the plus and the other one with the minus. Okay. And then just graph those. All right. And I think there was one more. Number 40. Let's look at number 40. And then we'll go on to new stuff. And just find the dy dx. Alright, so I'm going to rewrite this as, let me get a different color here. Now there's absolutely no way I could solve for y. One of the y's is inside a sign, the other is inside this complicated expression. So best I can do is d dx of both sides. When I take the derivative here, I get 1/2 this thing to the negative 1/2 times the derivative of the internal. When I take the derivative of sine of something, I get the cosine of that thing. Since these letters didn't match exactly, I have to tag on dy dx from the chain rule. Alright, now this derivative here is 1 plus 2y, since y and x are different, I have to tag on dy dx. Okay. So I'm going to get this dy dx right over here. I'm going to divide both sides by cosine of y. Is equal to, now I'm going to make this big fraction over here. On this side, the 2 is in the bottom. I can write that as to the negative 1/2. I can put that down in the bottom as a positive 1/2. This was in the numerator. Oh, hold it. This has a dy dx. Oh, I screwed up. Let me go back. Alright. I'm going to have to FOIL out, or not quite FOIL out, I'm going to have to distribute all of this to both parts, because I have a dy dx here and a dy dx here. So I'm going to have 1/2 when I distribute this into this one, the 1/2 and the 2 kill each other off. So I had to get rid of all the parentheses on the left-hand side, except for this one. That one's okay. And then on the right-hand side, I get this. Now I'm going to move this term over to this side. And I'll put what's on the right over here on the left. Okay, and then I'm going to factor out and then I'm going to divide by what's in parentheses. Finally, I will get and this divided by this. I could do 1/2 divided by and fractions within fractions, but it's a little cleaner if I do it like this. This right hand side really has a 2 in the denominator, and it has a x plus y squared to the 1/2 in the denominator. That's not rewriting the right hand side any differently, it's just alternate notation for that. And then I divide both sides by this. When I divide both sides by this will show up down here. And that would be it. Questions on number 40?
One question.
Yeah.
How would you be able to go up just a little bit
Mm-hmm.
and see how you took the derivative of x plus y to the 2 power, half power? I don't understand why God distribute into 2 different.
Okay. All right. I think you're talking way back here. And correct me if I'm wrong, but I think it's going way back to here. When I took the derivative of this, it's 1/2 this thing to the negative 1/2, then times the derivative of the inner function right here. When I took the derivative of this inner function with respect to x, I get 1 plus 2y dy dx. And then, now, since there's a dy dx over on the right hand side and a dy dx on the left hand side, I've got to get rid of these red parentheses. So I'm going to take all of this as if it's one item and distribute it inside the red parentheses to both of these. And then we get this big long thing here. Does that answer your question? Or did I answer a question that wasn't really your real question?
That was it.
Okay. Let's go on then to the new material. Inverse, exponential, and log functions. And we're going to start with a problem, and I'm going to have you follow these directions in your groups. So number 1, fold a piece of paper, ordinary sheet of paper, like your loose leaf paper, 50 times. Imagine doing that. Using intuition alone, you can't do any computations. Guess the thickness of paper that you're going to get. So if you fold it 50 times. So go in your groups. I'm going to give you a real quick 1 minute to do this, but just kind of share what you're in and then come to kind of a consensus for the group. All right. I'll give you a minute. Okay, 10 seconds more. All right, group 2, what do you have?
We just said it's going to be pretty thick if we do it like 50 times.
Pretty darn thick. Okay.
Yeah.
And let's go to group 3. What do you have?
I think it's an exponential function, right?
Yeah.
So I think we remember this from last semester. I think you
All
said
right,
something like,
hold on then. If you remember from last semester, I'm going to have you hold your answer. Okay.
okay.
You'll give it away. Thanks for revealing that. And then, how about group 4? You have
The distance from the Earth to the Moon.
distance from the Earth to the Moon. You're starting to
Yeah.
get there, but you're not close.
Oh.
It turns out to be even way bigger than that. It turns out to be approximately half the distance from the Earth to the Sun. And this might seem quite remarkable. And if you actually fold a piece of paper, take out a piece of paper and start folding it, if you want to, you'll probably only be able to fold it about, I think at most I've ever done it is like 7 times, and I needed some tools to help me to get that 7th fold. All right, and why does it become so incredibly, and now this is like if the papers were really together in a real compact way as well. Why is it so thick? Well, we can show this by this little chart here. Suppose I have 0 folds. So the number of sheets of paper thick is 1. And the thickness in inches is, and now I'm just trying, and this is my rough estimate. I just remembered, if I took like 400 sheets of paper, if I bought that to resupply my loose leaf notebook, it would be at least an inch. So I figured, and there's a very conservative estimate of the thickness of a piece of paper as 1/400th of an inch. Now, I converted that to miles, so it's a very small portion of a mile. Okay, now, every time you do another fold, it doubles the number of sheets. So converting this to decimal and then multiplying by 2, and this is just multiplied by 2, how many miles? And you see I kept doing this. Number of folds, 3, number of sheets, thickness, and I did it with X, so you can see the general pattern. It's 2 to the X, number of sheets thick, so it is an exponential function. So this is y equals 2 to the x. And this is exponential growth. And exponential growth is when, to get to the new value, you don't add something to a previous, you multiply your previous answer by something. And this COVID virus, does it have exponential growth? Yes. The base in the factor for the COVID virus, you see, like normally in the flu, what they say is if it's 1 to the x, so that means the number of infected people might be, we don't know. But if each person tends to give it to only one other person before the virus is done with them, then it'll stay, the number of people who have the virus will stay constant. So y equals 1 to the x would just be, if everybody who had it but always gave it to one other person, we would keep staying with the same number of people having the virus. It wouldn't have exponential growth in the number of cases. But this base for, normally for the flu, y is, it's a fairly small number. You give, one person gives it to, I think it's 2 or less people. But the COVID virus spreads more quickly. One person that has it tends to give it to around 3 people. So the base is starting to get kind of big. That's why, its spreading factor, it has a fairly big base to its exponential function. So that's why we've been so concerned that it could spread so quickly. All right, so the thickness in inches, you just take that many sheets and multiply it by 1/400th inches per sheet. And thickness in miles turns out to be this. And then when you get up to 2, the thing is 2 to the 50th is such a big number. If you've got a calculator, pull it out real quick and just go 2 to the 50th power, or a calculator on your computer. 2 to the 50th is 1.1 e to the 15. And my calculation is E15, so it means times 10 to the 15th. That's scientific notation. So 1.1 times 10 to the 15th, that compact notation deceives us. It's 1.1. We've got to move the decimal 15 places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And we got to put zeros in all these spaces. So there you'd have a million, there you'd have a billion, you'd have a trillion, quadrillion, quintillion, sextillion, or something. These are just such huge, gigantic numbers. That's why. And then when you convert this to miles, it's just gigantic. All right. Now, this exponential growth. So the topic is inverse, exponential, and log functions. We're starting with exponential. We're going to see the inverse of the exponential is the log function. So the exponential is the right place to start. Exponential functions grow incredibly fast. That's why in common lingo, when they say something like a rumor is spreading super fast, they'll say it has exponential growth. Well, that would happen if one person spread it to 2, each of those people spread it to 2 more, and so on. You get this exponential growth. You get bacteria, any living thing has exponential growth. The other common exponential growth that we're familiar with is money. When you invest money, you get a percentage return. Whenever it's growing by a constant percentage, then it's a multiplication factor for the growth rather than addition factor for the growth. So then it's exponential growth. So put your money in the bank, even if you're only getting 1% interest, that's exponential growth. All right, it is time for a break. So let's start again. It'll be 52. See ya in a bit. All right, we're going to start again. And I'm going to go to my camera. And use the whiteboard. And so the first topic is exponential functions. And when I'm teaching a college algebra class, what's very typical is students will think of, this is the right hand side of y equals x squared. This is the right hand side of y equals, let's say, 2 to the x power. It would start at 1 here versus starting at 0 over here. And other than starting a little bit lower, these look very similar. So students often, if I ask them which one grows faster, they're dumbfounded. They can't tell which of these two grows faster. But we would see y equals x squared, y equals 2 to the x. When x is 50, y is 2 to the 50th, which is gigantic. When x is 50, y is equal to 50 squared, which is not gigantic. So the picture is deceptive because we tend to focus near the origin. This is increasing a hell of a lot faster than this one over here. Exponential growth is just way more than any kind of polynomial type growth. Okay. And when we look at a basic exponential function, it looks like this. F of x is a to the x. And just review some of the basic facts. If a is equal to 1, then we have a constant function. It doesn't grow, it just stays. 1 to the x stays 1. If a is greater than 1, we have exponential growth. If a is less than 1, now here's the main thing though. We never use a less than or equal to 0. If a is equal to 0, then same as when a is equal to 1, we wouldn't really use an exponential function. It's just a constant function, either 1 or 0. If a is negative, we have a real problem. This thing would oscillate wildly between being negative whenever x is odd and positive when x is even, but is actually not really well defined, because you might consider like negative 2 to the third power. Well, that's really well defined because that should be negative 8. But you can rewrite negative 2 to the 6 over 2 power. And 6 divided by 2 is 3. But you see, both of these are even numbers. And so if you write it like this, you could be rewriting it as negative 2 to the 6th. And then you're taking the square root of that. And then you'd wind up getting positive 8. So it's not even clear whether the answer is going to be negative or positive. It depends on how you rewrite your fractions or your odd numbers and all that stuff. So besides, when the base is negative, and it would oscillate between positive and negative outputs, that doesn't have any application anyways. So we're not really, it's not of interest to us. So we just say we never let a be negative or 0. So if a is less than 0, when it's exponentially going down, we have a special name for this, is exponential decay. And probably they came about from, if you did look at like radioactive decay, as one of the applications of this. But it could be anything that, like if you're trying to get rid of mice, and every week, you have a huge mouse infection in your house. Every week you get rid of half of the mice. That's exponential decay. It's getting smaller and smaller and smaller by a multiplicative factor. Okay. And let me do a quick print screen. Here. Alright, so I'm going to go very quickly through a lot of stuff here, but hopefully most of it's a review. But if it's been a long time, you may need more of this than others do. Alright, let's talk about arithmetic growth. Versus geometric growth. Okay. If you have arithmetic growth, this means that it's linear. And if you're linear, you grow at a constant rate. You have exponential growth. Exponential growth is also synonymous with geometric growth. This is exponential. You don't grow by a constant rate, but something is constant. Grow by a constant. Does anybody know the word that's going to go here? It grows by a constant.
Multiple.
Was somebody saying something on that?
The word multiple.
You're on the right track. You're multiplying by something rather than adding something. And what we're going to call that is grows by a constant percentage. When you have a multiplicative factor, it causes, because if something grows by 100% all the time, what do? You just multiply it by 2 every time period. If something grows by 50%, you multiply it by 1.5 each time period. If something's growing by 2%, you multiply it by 1.02 each time period. And so you can see that as a percentage, grows by a constant percentage. So quick example over here is if I had eggs for my chickens. And if my chickens were, if I had 5 chickens, 5 female chickens, and they kept laying eggs every day, probably I'd get pretty much maybe 1 egg a day per chicken. Something like this, 5 eggs per day. So the number of eggs goes up by 5 every single day. It's growing at a constant rate. Geometric growth is, all I'd have to do is be letting the eggs hatch, and then they'd produce more chickens, which then produce more eggs. And then what's going to happen then is I'm going to get exponential growth instead. So my base from which it produces more chickens is growing as well, and I'd be doing this growing by a constant percentage. So when we have this one, we get something really cool that happens. We get a constant doubling time. The time that it takes for something to double, if you have a basic exponential growth, will remain constant. And that's really easy to see if the growth was 100%. Then every time period, that's the time period that you double. If your growth rate is 100% every year, then your doubling time is a year. But even if it's not 100%, the time that it takes for you to double will always be constant for a exponential function. The rough shapes of graphs. So let's go from here. Now shapes of the curves. For y equals a to the x, as long as a is greater than 1, the shape of the curve will always be the same. Now, one thing that's kind of unique about basic exponential curves, is you never go beneath the x-axis. Why is that? Because if you had something like, suppose it was y equals 2 to the x, or y equals 3 to the x, where the a is greater than 1. So whenever you raise a positive base to any power, you're always going to get a positive answer. If you raise a positive base to a negative power, so a couple quick things I want to review, because this could be a real source of misunderstandings if you're not refreshed on these. Negative exponents. 4 to the negative 2 power is 1 over 4 squared, 1/16. 4 to the 1/2 power is, the bottom number comes out, the top number stays in. Square root of 4, which is 2. 4 to the negative 1/2 power, combine them together. Do the negative exponent first. Negative exponent means bring it to the denominator. 1 over the square root of 4 to the first, so it would be 1/2, like this. Alright, so when you raise to positive powers or negative powers, you're going to get a positive result. All of these graphs, no matter what it is, if it's just y equals a to the x, no matter what the a is, they're all going to go through the same point of 1. Because anything to the 0 power is 1. All of them, when you go to the left, they will get smaller because you'll be raising them to negative exponents. When you go to the right, they'll get larger very quickly. So the basic shape is like this. And the larger the a, the steeper it goes. And if it more steeply goes up, it also more steeply goes down on the other side. Because if, for instance, if x was negative 1, you would get 1/2 versus you'd be getting 1/3 over here. So if you're tripling your money every day, you're going to go up very quickly. But you'd go backwards a day, you'd only have needed 1/3 of the amount of money to go up to 1. And so that's the basic shape if a is greater than 1. If a is equal to 1, of course, you're just going to get a horizontal line at 1. If y equals a to the x, if a is less than 1, of course, we're not thinking of negative numbers or 0. If that's the case, then it just reverses my graph. Like this. Okay. So this would be like this. Y equals 1/2 to the x. Alright, now, what this means is, this is like I'm trying to get rid of my mice problem. And every day I get rid of 1/2 of the mice that are in my house. So after day 1, there's half as much. Day 2, there's 1/4 as much, so on. But if I use negative exponents, it would reciprocate these, and so it would go up. Alright, now you won't often see them like this, though. More often, you'll see them written like this. But when you see an exponential function written with a negative exponent, you probably want to be rewriting it like this. And say, this is clearly exponential decay because the base is smaller than 1. Questions or comments? Okay, let me print this, print screen. Come back. Okay, now it may well be the case that all this feels like, oh, I'm really comfortable with this. I don't need any of this. Probably we're going to get to something though that you need some review. There's so much in this. Alright, let's go now to part 2, inverse functions. And logarithms. Okay. So, in a college algebra class, I might have a table like this. Here's my original function. Suppose it was f of x is x plus 4. Then I would have my inverse function. Now, the inverse, we can think of this function. One way of looking at a function, you may have never seen this before. One possible way is as a function machine. Any input comes in, and then it has one step to it. Add 4. So here's the function f. And then what comes out is x plus 4. So the function could be thought of as some input coming in, and the output is always going to be 4 bigger than the input. So if 10 went in, 14 comes out. You might think of this, if you were in a real crude way, if you put a length of something in, it lengthened it out and made it 4 units longer. Okay. Now, the inverse function the inverse of making something 4 longer would be making something 4 shorter. All you do is change the action word. Instead of adding 4, you subtract 4. Like this. And then we verify by taking f and f inverse together of something. And if I used, let's say, the number 10. Now, we were talking like this, so let me do it in this order. If I put 10 in there, f of 10, I made it into 14. F inverse of 10, I made it back to 10. And so what happens is these two kill each other off. And then you're just left as if nothing had ever happened to the 10 in the first place. Alright, so this is functions and inverse function and their relationship. And in a college algebra class, I go through and I put a whole bunch of functions like this down. And I put a function down and they figure out what the inverse function is. And they do the verification. The verification is more complete if we use x instead of a specific number, and then it would become x plus 4, and f inverse of x plus 4 is x plus 4 minus 4, and then the 4's cancel out, and the same thing happened. It's as if these two killed each other off. Now, we would do it for a whole bunch of different functions. And then I would put in this function, f of x equals 2 to the x, an exponential function. And what inevitably happens in a college algebra class is the students guess all kinds of functions. They say, oh, that's got to be the xth root of 2. And we try it and it doesn't work. How do we know that this doesn't work? Because when you take f inverse of f of, let's say, 3. F of 3 would be 2 to the third, so it's 8. But then this is the 8th root of 2, but these two things are supposed to cancel out, and you're supposed to get back to 3, and the 8th root of 2 is now 3, and it doesn't work. And so then they try all kinds of different things. And they tell me this function, and we try to find something that will invert this, and they never can find it because they've never known about logarithms. A special function had to be created that would actually do this, and it's a log function. So this one was if it's an exponential with base 2, it's got to be a log of base 2. And logarithms were created to to be the inverse of the exponential function. And then, if you did this, we would see that we would get the log, f inverse of anything is the log base 2 of that anything. And now this asks 2 to what power is 8, and that's 3. And now it's working correctly as if the f inverse and the f are killing each other off. So the inverse of an exponential function is a log function. As fast growing as an exponential function is, that's going to be as slow growing as a log function is. Grows fast, this grows slow. It still goes uphill, but it grows very slowly. And at this point, I have a question. And I'm going to have you go into your groups, and then I'll call on a group. The question is the inverse of every function a function? Or is it only inverses of certain functions that are functions? And to help you think about it, you can think about f of x equals x squared. And there's a concept that relates to this. And so go in your groups and talk about this and see if you can come up to any answer and any explanation that would help us out here. Is the inverse of every function going to be a function? And look at that one. All right, anybody need more time? All right, let me ask group 3. What do you have?
We said that not every inverse function is a function if you don't restrict the domain.
Aha, that's correct. We must restrict the domain. Is this one, if you take the inverse of this, will it be a function?
As long as they're not negatives.
That is correct. Very good. So this one, it turns out that the answer is no. It's the inverse of any function. The inverse of what we call one-to-one functions. Now, one-to-one functions. One-to-one we abbreviate with 1-1. And to be a one-to-one function, it passes the horizontal line test. The inverse of one-to-one functions are functions. But if the function wasn't one-to-one, then when you take its inverse, the new thing won't be a function anymore. And to explain this, we need to look at the relationship of an inverse function to its original function. So let me suppose I have a really, really simple function. X, f of x. This simple function just takes any input and triples it. Alright. The really simplistic way to look at an inverse function, it's always true. Every inverse function can be made from a table of a function, but all you have to do is flip around every input-output pair. All these outputs becomes inputs. All these inputs become outputs. An inverse function has to do exactly the opposite of what the original function was doing. It just reverses every pair of numbers. If it's making things 3 times as big, this is making things 3 times as small. All inverse functions do to tables is flip them around. Now there's a graphical interpretation of flipping around. What does it mean when we flip the point 3, 1 and turn it into the point 1, 3? When you do that, you will reflect it across the line y equals x. This gets taken to this right here. You go the same you go perpendicular to this line, to the line y equals x, the same distance, and it'll take you to your what's called your image point, right there. And if you take it, so 1, 3, or the red one was the original, and then the inverse was 3, 1. Or vice versa. 3, 1 takes you to red 3. So 2, 6. Goes to 6, 2. So it would send one of these perpendicular across to the other one, like this. Alright, so we take entire graphs and we can say, well, what's the shape of one graph? How does it relate to the shape of its inverse? Is you just reflect it across the line y equals x. So if we had a parabola, y equals x squared, it does not pass the horizontal line test. And if we reflected this parabola across the line y equal x, now to reflect across the line y equal x, points that strike the line y equal x don't move. This little arc gets reflected across, becomes this little arc over here. this part that's going up gets reflected across, becomes over here. This part winds up getting reflected across over here. You wind up getting a sideways parabola, which is no longer a function. It doesn't pass the vertical line test. When you reflect something that didn't pass the horizontal line test across the line y equal x, you will get something that won't pass the vertical line test. That's why we needed to have just one-to-one functions. So the way we typically deal with a function like y equals x squared is we turn it into a one-to-one function by like, hey, we only wanted the positive numbers anyway, or let's just take them one at a time if we wanted both the positives and the negatives. Let's just take this to be the case, and then we look for the inverse function. That way, and remember when you find an inverse function, how do you find the inverse function? First step is you interchange x and y. So you interchange x and y. And then, so that's what I've done here. Then you solve for y. To solve for y, I'm going to rewrite it. Y squared equals x. I'm going to square root both sides. Normally, when you square root both sides, you have to introduce a plus or minus sign. But I'm not going to put a plus or minus sign because I knew that my x was positive, so my y will always be just positive x. I won't have the other case. So y equals square root of x. I'm just going to get the positive sign and then replace the y with f inverse of x is the square root of x right here. So what's happening there is we restricted the domain to here, and that restricted the inverse to here, and now the inverse is a function. Okay. And let me print this screen. So we don't have much time to spend on logarithms, but they're the trickiest part of this. And there were some rules for exponents. And there's analogous rules for logs. The rules for exponents were really crazy. X to the a times x to the b is x to the a plus b. We're so used to this rule that we deal with it like it's no big problem, but it really is strange. There's no addition in the left-hand side. And the multiplication seems to magically turn into addition when you combine into one base. And similar thing happens in logarithms. And rule number 1 of logarithms is log base b of xy is, now that's one logarithm, just like this is one exponential function. And if we make 2 logarithms out of this, then the multiplication that was here seems to magically change to here. Now, if it's been a long time since you've written the rules for logarithms, you may have a hard time remembering this rule. What can make it really simple for you so that, like, 3 years from now you'll be able to remember it because you can reconstruct it, is you take a guess at what the rule is and then you just write a simple example. And this should make it clear. Suppose I had 2 to the 5th times 2 to the 6th. And I wanted to rewrite this as 2 separate logarithms. This would be log base 2 of 2 to the 5th. And this would be log base 2 of 2 to the 6th. Now, do I keep this multiplication a multiplication, or do I have to change it to addition? Well, we can tell by coming back over here. If I combine these two together, this is the same as 2 to the 11th power. Because visualize 5 2's, visualize 6 2's, there's 11 2's, there's 2 to the 11th. What we really had to do was add these two together when we put them like this. And that's how we get the 11th, and then this becomes 11. This is 5, this is 6, so it must have been the case that that was added, so that this is all in agreement. Alright, so that's rule number 1, logarithms. Rule number 2 is the same idea, log base b of x divided by y, but applied to division. Log base b of x minus log base b of y, and rule number 3 of logarithms is log base b of x to the r, as the r gets to come out in front, and it looks like this. And there's one other rule for logarithms, but it doesn't have a number. It's so important it has a name. Does anybody remember the name of the last rule for logarithms?
The change of base.
Change of base. Log base b of x, as we get to make up any new base that we want. Log base c. And the x was up above the b, closer to the ceiling than the b is. And b is closer to, so this one stays higher, and this one is lower. But we have the new base c right over here. Now, the c that's typically chosen is either base 10 or base e, because those are the only logarithms on most calculators. And so we change to one of those with the change of base formula. Alright, so the analogous rule for exponents was here, was x to the a over x to the b, x to the a minus b, and the analogous rule here was x to the a to the b. Power to a power multiply. And that's what's actually happening here. If you think of the log is really an exponent, it's the exponent that you have to place on the base to get to this. Then you're taking an exponent and you're raising it to another power. So power to a power you're multiplying makes this rule a little more understandable. And so let's run to a problem. Print the screen. Suppose I have solve 2 to the 3x minus 1 is equal to 3 to the x. All right. This is a tough problem to solve because the x is in an unnatural place. It's way up in the exponent position. So what I want to do is bring it down from the unnatural position. If I can bring it down, I think I can solve for it. So, but there's no rules that allow me to bring it down from the exponent position except rule 3 of logarithms. But there's no logs in this equation. Well, we can introduce logs. And we can take the log. Let's take the ln of both sides. We'll be preferring base e whenever we do logarithms or exponential functions in calculus. So let's start getting you used to that. ln of 2 to the 3x minus 1, ln of 3 to the x. Alright, now I'm going to use rule 3 of logarithms. And that allows me to move the exponent down out front. X minus 1 times ln 2 equals x ln 3. Now, I just made a mistake that I see students have made this mistake many, many times over the years, so I kind of want to draw attention to it. Does anybody see the mistake that I made? Pipe in if you see it. All right.
Are there no parentheses?
That's correct. Without the parentheses, this ln2 would only be multiplied by the 1. It's got to be multiplied into both of those. So it's got to be there. All right. So then, now I'm going to solve this thing for x, and I distribute the ln2 to both. 3x ln2 minus ln2 x ln3. And now I've written 3 terms. 2 of these terms contain x, and 1 term does not. So I'm going to move the terms that contain x over here, all the terms that do not over here. Now, I'm still trying to solve for x. But x is written twice. As long as it's written twice, I can't isolate it. So how do I write it just once? I factor it out. And then I'm going to divide by what's in parentheses. This is what I call my exact answer. And when I punch it out in my calculator, I'll get my approximate. Neither answer is better than the other. If you're going to Home Depot and you're telling them how long to cut your piece of wood, you better not give them the exact answer. Tell them 3.46 inches. But if you're giving this answer to NASA and they're sending somebody to Mars, you better give them this answer so they can get as exact as they need to. And now, print. All right, real quick, if I had this equation over here, so I started with log x equals 3. All right. So there's an unwritten base. When you see the word log, it means base 10. To get rid of the logarithm, a really quick way to do it is put a giant base underneath it. And what happens then is 10 and log base 10 kill each other off, they're inverse functions, and you get 10 to the third, or x is equal to 1,000. Like this. Alright, your homework is 1.3, reviewing exponential, logarithmic, and inverse functions. And I will see you all tomorrow, Thursday. Any questions? And Kylie, you'd mentioned something about after class. If you want to stay after for a little bit, I'd be happy to work with you.
Yes, please.
All right, great. Anybody else that wants to see what she's asking is welcome to stay as well. But I'll see you all on Thursday. Let me stop the video.